This lesson is on solving for the pH of an acid-base titration involving a weak base, C6H5NH2 or aniline. Aniline C6H5NH2 is a weak base with Kb equaling 3.9 times 10 to the minus 10. Consider a titration of 25 ml of 0.10 m C6H5NH2 by 0.10 m HCl. Answer the following questions. A. Write out the reaction associated with Kb. B. Calculate the pH after the following total bonds of HCl have been added. 1. 0 ml, 2. 12.5 ml, 3. 25 ml, and 4. 35 ml. The net ion equation with respect to Kb is C6H5NH2AQ plus H2O at equilibrium forms C6H5NH3 plus AQ plus OH minus AQ. The first problem is to calculate the pH after 0 ml of 0.10 m HCl has been added. To solve this problem, one needs to construct a Rice table. The initial concentration of C6H5NH2 is 0.10 molar, and for C6H5NH3 plus and OH minus are both 0. The change is minus X for C6H5NH2 and plus X for both C6H5NH3 plus and OH minus. The equivalent concentration is 0.10 minus X for C6H5NH2 and X for both C6H5NH3 plus and OH minus. The equilibrium expression is the concentrations of C6H5NH3 plus times OH minus over the concentration of C6H5NH2 equals X squared divided by 0.10 minus X is 3.9 times 10 to the minus 10. To determine if X is small enough to ignore, we take the ratio between aniline's initial concentration and Kb to determine if it is greater than or equal to 400. It turns out that after doing this, the ratio equals 2.6 times 10 to the 8, which is greater than or equal to 400. So the assumption X is small is confirmed. The revised equation is X squared divided by 0.10 equals 3.9 times 10 to the minus 10. And solve for X, take the square root of the product of 0.10 times 3.9 times 10 minus 10 equals plus or minus 6.2 times 10 to the minus 6 molar. Using only the positive root, X equals 6.2 times 10 to the minus 6 molar. The pOH of this solution is by taking the negative log of 6.2 times 10 to the minus 6, which is 5.20. The pH of this solution equals 14 minus pOH, or 14 minus 5.20 equals 8.80. The second problem is to calculate pH after 12.5 ml of 0.10 m HCl has been added. Note MO equals volume in milliliter times molarity in units of moles per liter. The construction of an MO stoichiometric table is performed. The MO of C6H5NH2 is by taking 0.10 molar times 25 ml equals 2.5 millimoles. The MO of HCl plus is by taking 0.10 molar times 12.5 ml equals 1.25 millimoles. The amount of HCl plus is the limiting reagent, so after subtracting both sides by 1.25 millimoles and adding 1.25 millimoles to C6H5NH3 plus results in a final amount of 1.25 millimoles for C6H5NH2 and C6H5NH3 plus. The molarities of both C6H5NH2 and C6H5NH3 plus are 0.33 molar each. Since the molarities of C6H5NH2 and C6H5NH3 plus are both equal, under the Hansen-Back equation, log of the ratio between the concentration of C6H5NH2 and divided by C6H5NH3 plus equals log 1 or 0. Ka of C6H5NH3 plus equals 2.6 times 10 to the minus 5. Therefore, pH equals pK, or the negative log of 2.6 times 10 to the minus 5 equals 4.59. The third problem is to calculate pH after 25 ml of 0.10 m HCl has been added. The construction of an MO stoichiometric table is performed. The MO of C6H5NH2 and H3O plus are by taking 0.10 molar times 25 ml equals 2.5 millimoles each. The amount of C6H5, NH2, and HCl plus are both the limiting reagents, so after subtracting both sides by 2.5 millimoles and adding 2.5 millimoles to C6H5NH3 plus results in a final amount of 2.5 millimoles for C6H5NH3 plus. The molarity of C6H5NH3 plus is 0.050 molar. At equivalence point, one needs the Ka of C6H5NH3 plus. Ka of C6H5NH3 plus is by taking Kw over Kb, or 1.0 times 10 to the minus 14 divided by 3.9 times 10 to the minus 10 equals 2.6 times 10 to the minus 5. To determine if one can assume X is small to ignore, one takes C6H5NH3 pluses initial concentration and divide by Ka to see if the ratio is greater than or equal to 400. The ratio is 0.050 divided by 2.6 times 10 minus 5 equals 1923, which is greater than or equal to 400. Thus, the assumption that x is small to ignore is confirmed. The revised equation is Ka equals the concentrations of C6H5NH2 times H3O plus divided by C6H5NH3 plus's concentration, which equals x squared divided by 0.050 equals 2.6 times 10 to the minus 5. The final value for x is plus or minus 1.1 times 10 to the minus 3 molar. Using only the positive root, x equals 1.1 times 10 to the minus 3 molar. The pH of this solution is by taking the negative log of H3O plus, or negative log of 1.1 times 10 minus 3 is 2.96. The fourth problem is to calculate the pH after 35 ml of 0.10 m NaOH has been added. The construction of an mmol stoichiometric table is performed. The mmol of C6H5NH2 is by taking 0.10 molar times 25 ml equals 2.5 millimoles. The mmol of H3O plus is by taking 0.10 molar times 35 ml equals 3.5 millimoles. The amount of C6H5NH2 is the limiting reagent, so after subtracting both substances by 2.5 millimoles and adding 2.5 millimoles to C6H5NH3 plus results in a final amount of 1.0 millimoles for H3O plus and 2.5 millimoles for C6H5NH3 plus. The molarities are as follows. H3O plus is 0.017 molar, and for C6H5NH3 plus is 0.042 molar. One can determine the pH of this solution since H3O plus is in excess. The pH of this solution is by taking the pH of negative log of H3O plus or negative log of 0.017 equals 1.77.